Okay, so I'm going to repeat a little bit because of the recording. So now the question is that, as I told you, that based on these sample mean, sample proportion, what do? We extract the mean distributions, right? Sampling distribution of the sample mean, sigma mean, standard deviation mean, variance mean, right? So all of these are known as a different sampling distribution of mean, standard deviation, and blah 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 blah. Now, so depending on the statistics, we are doing the sampling distribution. If we are interested in means, then we're gonna do that one. How are we gonna do that? Let's take an example. Let's take a simple example. Now we have a uniform probability distribution, right? And this is a probability distribution. From here, we're gonna extract the sampling sample distribution, right? So the probability distribution is uniform. What does that mean? We know that. What does that mean, right? You know what does uniform mean. Uniform means that whatever the value of a random variable, right? Whatever the value, what is uniform distribution? That's the uniform distribution, right? How do we explain this? Whatever the value of a random variable, the likelihood of occurrence is same, it's equal. The likelihood are the chances of occurrence is equal. Then it means uniform. So if we have x1 is 1 and x2 is 2, so we have all the x's here, 1, 2, 3, 4. So all of them have an equal. So let's say, what does that mean? That if it's equal, so random variable x is representing, let's take an example. Random variable of x is representing the number of errors in a work population, in a working place, in a company. There are different people, and all of them can make errors, right? For example, my staff, I have a company and there are little different people working on that, and every day they make some mistakes, right? So let's say population size is n is 4. So if n is 4, when we construct the distribution, so all these 4 having the equal chances of making an error, right? All of these 4 are making errors in their work, right? And they are uniformly distributed, means equal chances. So what is the chance of x1? 1 by 2, 1 by 4. x2, 1 by 4. x3, 1 by 4. x4, 1 by 4. Right? So all of them, this is a population. Remember, capital N is 4, right? We are not talking about sample at this moment. So we are just talking about the population distribution. And when we draw this distribution, it comes out that every population member has 0.25 probability. Probability of x equal to, oops, why is doing this way? So probability at every point here probability of x equal to xi, which is from 1 to 4, is 0.25. for everyone, right? So it's the same. So that we're gonna draw this kind of a distribution. Now, if we take the measures of the population means mu, so what will be the mu? Mu will be sum of xi upon n. What is sum of x? So let's say x is 1, 2, 3, 4, right? Or in a better way, we can draw a tabular form. So what is x? 1, 2, 3, 4. What is sum of x? What gonna be sum of x? Sum of x gonna be 10, right? So sum of x upon n, so you can do it like 10 by 4, right? Which is again give us 2.5. Do you understand? So this is 10 by 4, which is 2.5. That's our population mu. Similarly, you can extract the sigma, standard deviation. Now recall that we have here capital S and small s, right? What is the capital S? Sum of what is the capital S? Sum of x minus x bar square divided by n whole under root, right? And what is the small s? Sum of x, the upper in the numerator, the x minus x bar is same, but in denominator it will be n minus 1. Now what is this? Just remember that this shows the biasedness, that this standard error is biased, and this small s shows unbiasedness. And of course, for a better, this is small s, this is capital S. And for sure, for an efficient estimator, it should be unbiased. We will see later on the difference between biased and unbiased and what are the properties, right? So our estimator should be unbiased, that's for sure. But now we just calculate the based on the capital S, right? What is the difference between biased and unbiased? That, as I told you, that we will take care of it later on. So now we follow this one, sum of x minus x bar square upon capital N. Now, if you solve the same thing while constructing that distribution, which is 1, 2, 3, 4, and then you can have mu, which is 2.5. We already have extracted. Now here you can extract x minus mu square. So 1 minus 2.5 is minus 1.5 square, right? It's 0.5 square. It's 1.5 square. It's 0.5 square. Yeah. So when you calculate it, you can sum it and you can divide it by n, you can get this 1.12. Now remember, keep in the mind that why do we need this? Remember that mu is 2.5 and sigma is 1.12. Now we will go further. We get the measure value of a populations, right? So these are the parameter values of a population. Now we will take the sample from the same population. Here n is 4. From this 4, let's take out the sample. Small n is 2. We take 2 people and we see different combination. We see how many errors they make, right? So all possible samples, how many? 2. Because with sample size n equals 2, it means that here sample size is 2, means that we are selecting 2 people Yeah, we are selecting two people at a time, and we are going to see all the possibilities of combination of these two peoples, right? It can be one and one because there are total four people. Let's say their identity, their registration number is 1, 2, 3, 4. So first I will take a student, if they take a person with a registration number with 1, and the possibility with itself is 1, right? So second observation is also 1. So of course I'm going to take it with replacement. So once I pick it, I will ask them to go back, right, into the room. And there is a possibility that the second time, the both time I recall the same person. So we are selecting two people at a time, and we are going to see all the possibilities. So that means we are collecting the sample with replacement. And it further elaborates us that we can have how many total samples? 16 samples by picking two combinations of two different, by picking the combination of two different people. All right. So the total sample will be, how do we know that total sample? You have already done this. You get this 16 by this formula, n power n. What is this? This is the possibility of combination, which means total samples. Total samples with sample size n equal to 2. So don't confuse it. This is not population. This is a sample statistic. Now, we know here n is 4. So 4 power 2 is 16. That's how we get it. Right? Okay. So now these are the combination we can draw. We pick two people, they commit one commit error, one commits one error first. So first person committed one error, and the second person also committed one error, right? So this is the number of errors. So there are four people. So when I pick first person, so he's making one error, the second person is also making one error. So then there is a possibility that the first person makes two error, and the second person make only one error. So one error, first person makes one error and the second person makes two errors. Then first person makes one error and the second person makes three errors. So there are total 16 ways these two people can make different errors, different kind of errors, right? So what does that mean? That means there are 16 ways that two people can make errors, right? And what are these? These are these. Now instead of this, instead we created the distribution of the actual population. Here we are collecting the sample mean. So here we draw another 16 sample means. For each observation we can have each sample mean. So I just added 1 plus 1. In population we calculated sum of x and from the population, right? So here I take 1 1 and I added up them, and it's 2, and divided by 2 is 1. This one is 3. So I calculated these means in the same way, right? Now, what is the shape? Remember, in population, the shape of a distribution was uniform, right? So what will be the shape here? 16 sample means will be in this table. The same number can be repeated. Now, you can see that these two combination, they are making the same mean, sample mean, right? Now, what we have done, we calculated each sample means based on this population dynamics. So instead of drawing the possibility distribution, which we have observed that it was uniform, right, in case of population. Now, if we construct this probability distribution, then what will be the shape of that probability distribution? How do we that? How do we do that? We can do that through histograms. And how we gonna make a histogram? Of course, we're gonna make a frequency table. So how many things? There's one. Why do we have one? 1.5, 2, 2.5, 3, 3.5, 4. That's it. Right? So let me draw on this side. 1, 1.5, 2, 2.5, 3, 3.5, and 4. 1, 2, 3, 4, 5, 6, 7. Right? How many times 1 has been repeated? 1 time. How many times 1.5? 2 times. How many times 2? 3 times. 2.5? 4 times. 3? 3 times. 2 times. And 1 time. So total, how many samples? 16. So what is the probability distribution? 1 by 16. 1.5 by 16. Sorry, 2 by 16. That's 2 by 16. That's 3 by 16. That's 4 by 16. And the last one, sum of probability is 1, which is 16 by 16. So that's the probability distribution against the sample mean, X bar. Is it clear? Is it clear to you so far? So once I made this, you can make a histogram. All right, so that's the histogram. So what is the probability of 1? Is 1 by 16, which is this much amount in decimals. Right, so from this sampling distribution, what does it look like? It looks like a symmetrical shape. It is having a symmetrical shape, right? So this is, remember, this is the X bar shape. Now, if we compare the population, what do we get? We have population and sample, which is uniform, and here it's normal distribution. Or symmetrical distribution, right? Means everything is equal. Now, what is the logic? Let's discuss a bit. But first, let's take the mean of a sampling mean. So what will be the mean of a sampling mean? That will be mu X bar. Right? So in this case, it will be one. We have already drawn like the frequency table. So from that frequency table, you can just add up the values of x bar 1, x bar 2, x bar 3. So just like this, just like this one. So this one, 1.1, 1.5, 2, 2.5, 3, 3.5, and 4. These are the values, right? You add up this, and how many values? 1, 2, 3, 4, 5, 6, 7. You can just simply, you don't need to extract the through probability distribution, right? So you can just simply just using the same formula as for the population, uh, you do it all, you sum up all these things, right, making the table probability. I think it was like 1, 2, so on. I mean, you can solve it by yourself, and what will you get? You will get 2.24, 2.5. Now remember, the population mean was also 2.5, right? So this means there is no difference between the population mean and the sampling mean. I mean mean of a sampling mean. So if this is the case, then we call that this is now unbiased. We have no bias in it. This is an unbiased estimator. So mu of x bar. So x bar is an unbiased estimator of a population, which we are looking into. So it's the same as the mu of population as a mu of sample. Do you understand this? So always, it's always the case. This one is always the case. Whatever the population you take, the population means is should always be equal to the sample mean, right? And this shows the biasness. Now when we come to the sigma, now we already have distribution of x bar. Let me make it clear once again. So what does we have? We have x. What is x? 1, 1.5, 2, 2.5, 3, 3.5, 4. And we have distribution 1, 2, 3, 4, 3, 2, 1, right? So that's the probability. 1 by 16, 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 1 by 16. I mean like the value of 16. This is a probabilities distribution. So sum of xi pi. This is also expected value of x bar. So here I'm talking about x bar. So you can just sum up this and you will get 1 right here. So just multiply with this probability 1. So it will be 1 by 16. So 2 times 1.5. So it's 3 by 16. 3 to 6 by 16. 4 to 8, 8 and 10 by 16. Right, so 3 by 16. Again 6 by 16. 3, 3, 9, 9 by 16. 9 by 16, and this one is 7 by 16, and this one is 4 by 16. So you can add up and you can get the 2.5, right? Now you have this one and this one. Now when we come to the mean, we know we are using the same formula of x bar, and now we have x bar, this one, yeah. So you subtract 2.5 from each one of this distribution, 1 minus 2.5, 1.5 minus 2.5, and everything, right? And then take a square and divide by n. What will you get? 1 minus 2.5 square plus 1.5 minus 2.5 square plus so on, so on, so on, up to 16. And you will get 0.79. Now, if you remember, if you recall, this was equal to mu population, but our sigma population Population for standard deviation for population was 1.12. Remember? I remembered. So here it's 0.79. So this means that sigma x bar, this means that sigma x bar is not equal to sigma. It means it's unbiased. Oh, sorry, it's biased. It's not that efficient, right? So if we take, what is the relation? What is the relation between the sample standard deviation or standard deviation of a sample mean and the population? It's simple. If we do this, that's the relation. The relation between mean of a standard deviation of a mean is population divided by under root n. If you do this, then it will give you the same answer. Now remember, this is not the population one, this is the sample size n. So what is this? Sigma was 1.12 divided by root. A root of what? What is the sample size? Our sample size was 2. Right? So if you solve this, you will get the same result, 0.79. So in any distribution, when we calculate the sampling distribution of a mean, mu x bar equals to mu, and sigma x bar should be equal to sigma upon n. Right? Now, coming to the properties of a sampling distribution. I will come to this later. First, let's talk about the properties. As I told you about the biasness and unbiasedness. What is unbiasedness? When mu x bar equal to mu, then it's unbiasedness, right? And in other way, it's biased. Yeah. So if it's not equal, then it is biased. So basically, this one is biased distribution because here it's not equal, right? So this is population. Oops. Can you hear now? Hello, can you hear now? I hope you can hear me now. Wait. Can you hear me now? Okay, I hope that you can hear me now. Because some of you just sent me a message that you cannot hear me. Okay, anyway, let's continue. So what is this? This is biased, right? This is not unbiased. Because here it's not equal. Here it's not equal, right? So this is a point. where it's mu of x bar and this is mu. So in this case it's not equal, so it's biased. Otherwise it's unbiased. If it's same, right? If this one is also same, then this one, then it's biased, because here mu x bar is equal to mu. So that's the first property of unbiasedness, that mean of a sampling distribution equals to the population means, right? Now, if not equal, then it's biased estimators. Mathematically, we can write it as well, ex bar equal to mu. Means every expectation of a sample statistic is equal to mu. Similarly, es square is equal to sigma square. If this is the case, then it's biased. If not, then it's unbiased. So we have seen that it's unbiased in terms of a sigma. So that's the first property of a sampling distribution, that unbiasedness. Is it clear for you what is unbiasedness? Now, next is efficiency. Efficiency means that mean is better than median. Sample mean is efficient compared to median. It is efficient because it's closer to the population mean. So you see, this is the population mean. So this one is the sampling mean, right? Sampling distribution of mean. This one is sampling distribution of median. And if you see, it's farther. This is closer, and this one is farther, right? So that's the difference. That's known as efficiency. So we say that mean come closer to the population mean than any other unbiased estimator. Third thing is about consistency, right? Similarly, sampling distribution mean is more consistent mean because it consistently provides the solution against the population parameter as the sample size increases, right? Or decreases, other way around. What does that mean? Here, sample size is A, this is closer. Sample size, smaller sample size is closer. This sample size is farther. So as sample size increases, variation of a sample mean from population mean decreases, right? So that's the third one, consistency. So I think this is enough for today's lesson. From tomorrow first we will talk about the sampling distribution, that how the standard deviation of all possible sample means, x bar, it's scattered, and then population standard deviation. We already talked about, sorry, this one we already talked about, that the mu 2.5 and sigma this and this one and this one. We already talked about this. Next week we will do this. We will try to prove these properties of unbiasedness, right? Then we come to the central limit theorem, and then we will go further as well. So it's not finished, so we will talk further. I think that's this one. That's for 17th November. All right, so this one we will talk about next class, when we will try to finish this sampling distribution, and we will solve some question as well.